You realize that I'm not very keen on my theory. I see. The year end nice. The theory is nice, but it's also, of course, it's very pretty. Understand it. Things make sense. But I don't know, yeah, that's why I don't understand half of the times. I don't know. Exactly.
A little bit of attrition.
Yeah. I know some people have to travel actually.
I don't know.
I look up to
Okay, well, welcome everyone to the last talk of the Wisconsin School for Quantum Science. Thanks to you guys that have stuck around. Today, yes, Robert will give us part 2 of the talk he started on Wednesday morning. So I'm very excited to hear the current status of superconducting qubits, but also Robert will tell us a little bit about what life is like being in a quantum startup. That will be the latter part of the talk. I think there will also be a lot of insights that will be useful for you guys there. So thank you very much, Robert.
Okay, great. Thank you. Yeah, so last time I gave you an introduction to the basic physics, described how we can use a superconducting integrated circuit to implement a qubit. I talked about single qubit operations, gave you the basics of measurement. So today I'm going to continue with some of the important baseline information so you can understand what the critical issues are for scaling to utility size processors. So I'll talk about coupling of qubits a little bit. Then I'll focus on some of the work that we've done here in Madison on developing scalable approaches to control and measurement. But then in the second part of the presentation, I'll tell you a little bit about a new activity that's happening here on campus, a startup company called CoLab that I'm involved in. And the path we're taking to build something useful with superconducting quantum processors in a small number of years. Before I get into this, do you guys have any specific questions that came out of the material I presented a couple days ago? You're content? Okay. Well, let's get into it. So I've described how superconducting qubits are nonlinear microwave modes that involve capacitance and an inductance that's realized using the Josephson junction, and it's the nonlinearity of the Josephson inductance that allows us to make qubits. And what's critically important about this system is that these are large objects. And in the early days of this field, 20 years or so ago, a lot of people would say this is crazy, this is a huge liability. You have so much real estate that's taken up by one of these objects. How are you going to get a large number of qubits on a single substrate? But actually, that's the completely wrong way to think about this. The fact that these qubits are large is actually a huge advantage, because there needs to be a good match between the size of the qubit and the size of all of the control wiring that you need to get to the circuit. Otherwise, you know, scaling is just hopeless. And so maybe you've heard a little bit about quantum dots earlier in this session, and there's been a lot of progress on that front, for sure. But, you know, one of the problems here is these devices are so small that it's difficult, if not impossible, to get the number of control lines you need to do high-fidelity operations down to address the individual qubits. So, you know, the fact that everything is big means that we can do the escape wiring for control and measurement. We can do this in a sensible way, and everything becomes, you know, pretty comfortable. So the devices are, you know, roughly millimeter in scale, and that means that they've got very large electric dipole moments, so that coupling between qubits is easy. In other qubit implementations, atoms, ions, you know, the coupling is the hard part. In the superconducting world, coupling is easy. What's hard is figuring out how to turn coupling off. And I'll tell you how we do that. But, you know, again, because these objects are so large, coupling is very easy. And these are electrical circuits. You know, there's these exotic quantum objects, but at the end of the day, they're electrical circuits. So we think about coupling in very simple electrical circuit terms. To get qubits to interact, you can couple them together with capacitors or inductors. And so here's an example of a very early experiment that I did over 20 years ago. This photo is not from that experiment. This is more a recent photo, but it gives you the basic idea. You have two qubits on a single substrate, and you just have some separation between them. There's going to be some pad-to-pad capacitance that's going to allow you to implement entanglement gates. So when you have two electrodes connected by capacitance, classically you can write down the charging energy associated with that structure. It's going to be like the product of charges on the two pads. And quantum mechanically, indeed, you get an interaction Hamiltonian that looks like Q1 times Q2, the charge on qubit 1 times charge on qubit 2. Now remember, charge we can map to creation and annihilation operators. Charge operator is like A minus I, A dagger. So when you have this product of charge operators, you get terms that look like, say, if A dagger are the creation and annihilation on one qubit, B dagger creation and annihilation on another qubit. You get swap terms that look like AB dagger, A dagger B. So you can exchange quanta between the two modes, and you know, indeed, you can map this interaction Hamiltonian, which is just the charging energy, the coupling capacitance of two pads. You can map that to this swap interaction where qubit 1 can exchange energy with qubit 2. So you can do a very simple experiment where you take these two qubits, which remember are tunable in frequency. If we implement this Josephson element using a squid, which you can think about as a flux tunable Josephson junction, then we can tune the effective inductance of the mode to adjust the mode frequency, and so we can bring devices in and out of resonance. You can create an excitation in one qubit, quickly, non-adiabatically bias it into resonance with another qubit, and then you can let these two guys exchange energy and implement swap operation or square root of swap operation, for example, to implement some kind of entanglement gate. So that swap interaction is one of the two basic entangling interactions, kind of native entangling operations that you get in the world of superconducting qubits. The other nice native entangling interaction that you get is a controlled phase interaction that something was first proposed in the context of phase qubits over 20 years ago by a group of Fred Wellstud. This, to my knowledge, I think was the first implementation of this C-phase interaction in the context of a transmon qubit. And the basic idea here is to exploit the excited non-computational states of the transmon qubit. So you remember, because we've got this cosine potential coming from the nonlinearity of the Josephson inductance, you get a 0-1 transition frequency that's some value, and then you have a smaller transition frequency that'll take you from the one state to this non-computational 2 state. So if you have 2 qubits, you're going to have energies 0, 1, 1, 0. Then you can have, here, let's do this. So you've got these indices, as I remember, this is the first index versus 1 qubit, the second index versus another qubit. You can have both qubits in the ground state. You can have single excitation in each qubit, and these qubits can be at different frequencies. So maybe your qubit B is at a higher frequency than qubit A. You're going to end up with a 2-0 state. You're also going to end up with a 0-2 state, but you're also going to have a 1-1 state where the qubits are each in their excited state. And you can exploit level repulsion between 1-1 state and 0-2 or 2-0 to do an entangling gate. So, and how to put this in simple words. Let's say that if you were to fix the frequency of one qubit and tune the energy of another qubit, you would find that the 1-1 state disperses in energy in some way that we can, understand from the, say, the flux dependence of the critical current of that qubit. And in the absence of interaction between the qubits, as you vary the frequency of one of the qubits, the system is going to accumulate phase in some way that we can predict and control. But then if you've got this, an interaction between 2 qubits, you can end up with level repulsion between the 1-1 state and the 0-2 state. That will cause the system to accumulate phase at a different rate depending on whether or not your control qubit is in the excited state. So it's a very simple way to implement this type of Hamiltonian, where you tune the frequency of one of your 2 qubits, and depending on whether or not the other qubit is excited or not, you're going to acquire a different phase. And this could be the basis of an entangling gate. You know from basic quantum mechanics or simple quantum information theory that it's straightforward to map between C phase and C naught, and either one of those is going to be a universal entangling gate. So this is the basis of a very nice entangling gate that can be executed with fidelity that's in the 3+9s range currently, 99.9 or 99.9 and a bit. So groups at Google have done this. This is the basis for quantum supremacy experiment about 5 or so years ago. This approach is continued to be pursued by the Google group, and the national effort in China is also using this scheme to implement high fidelity entangling gates. Gate times are about 30 to 40 nanoseconds typically. A small fraction of the state-of-the-art coherence times, which now are about 100 microseconds, 100 to 300 or so microseconds. So that ratio of coherence time to gate time, that's a pretty good figure of merit. So in this initial implementation of this C-phase gate, this is from the Shulkup group at Yale, this was done just with 2 qubits that interacted directly via capacitive coupling without any intermediary element to modulate the coupling string. That's great. You can demonstrate the basic elements of this gate, but it's critical to be able to turn the coupling off. And so a very nice approach to controlling coupling between these qubits is to use this circuit that's shown here. This is actually a cartoon taken from Lincoln Labs experiment. So here what you do, you've got 2 qubits that have some direct coupling, G12, and they can couple directly via capacitance, but in between you stick another circuit element that you can tune. And so think about a charge on qubit 1 that can induce a voltage on qubit 2 via this interaction capacitor, coupling capacitor C12, but there's this separate coupling path that goes along the black lines, and here you've got some mode that connects this node to ground. And this is a resonant mode, and so above the resonance, the connection from this node to ground looks capacitive, and below the resonance of this mode, that connection looks inductive. And so it turns out by tuning this mode, you can tune the coupling along this arm from looking like a capacitive coupling that kind of adds constructively with the coupling you get from this linear capacitance. You can tune from like a capacitive coupling to an inductive coupling that has a different sign. And by adjusting the balance of the direct coupling and the coupling mediated by this tunable coupler, it turns out you can modulate the interaction all the way down to 0. And that's what you need in order to do high fidelity gates. Again, the hard thing isn't turning on interaction between qubits. The hard thing is figuring out a good way to achieve a really accurate off state. And so it's important to be able to tune all the way through 0. You know, another thing you can do to suppress interaction between qubits is to just detune the modes. So if you have qubits in 2 different frequencies with detuning delta and some interaction strength G, then you can do perturbation theory, and you see that if their qubits are detuned, you're going to get an interaction that goes like G squared over delta. And if qubit detuning is very large compared to G, you can say, okay, well, let's suppress this interaction by some large factor. But you know, when you think about what you need in order to build a practical quantum processor, it's not enough just to be able to detune qubits. You need to have a way really to turn the coupling between modes all the way down to 0. And this trick of using a separate mode, which looks for all the world like an additional qubit, I mean, this is the right way to do this. So this is a circuit that we're looking at in my lab at the moment. It was designed and fabricated by grad students in my group. And it's just got 2 qubits and 1 tunable coupler. So it's a very simple circuit. But our focus right now is not to just stamp a bunch of these qubits on a substrate and scale up to large numbers. That's easy to do. The hard thing to do is to figure out how to do extremely high fidelity gate operations. And I'll give some arguments for why this is a good target in a few more slides. But it's really critical if we want to achieve utility scale. It turns out that you need to get gate infidelity down to about the 10 to the minus 4 level. And that's hard to do. Current state of the art is around 10 to the minus 3. So we're asking for another order of magnitude improvement in fidelity. But I think it's doable, and we're taking specific steps to reach that. What we really need to do is, before we put a bunch of effort into scaling very large system sizes, we need to, ensure that we can achieve these extremely low infidelities. So there are a couple of important pieces of engineering that go into the circuit that I don't have a ton of time to get into. We've actually figured out a very nice way to reduce DC crosstalk between these modes, down to, I think, unheard of values. And that's important because as we go to larger system sizes, every time we control one qubit, we need to make sure that we're not kind of perturbing the mode frequency or the state of neighbors. And so there's a DC crosstalk we need to worry about because that affects the frequencies that all these qubits resonate at. But then at the same time, we have to worry about microwave crosstalks. We're also doing very careful characterization of microwave crosstalk here. I think we've got a very good handle on this. So here you can see you get one large patch for qubit 1, one large patch for qubit 2. There's a direct capacitive crosstalk between these 2 qubit patches, but you've also got this coupler that sits in the middle, and there's an indirect path where interaction between the 2 qubit modes is mediated by the coupler that sits in between. All of these devices are flux tunable. The purple lines are flux tuning lines that are kind of special in order to suppress crosstalk. They couple to these squid loops that look like 2 little pointy nubs that come down to the drive line. And then there are some separate microwave control lines here for charge gates, XY gates, shown in yellow. We can also do microwave rotations through the flux line. And these grayed out elements on the top are local readout resonators that we can use to probe the states of the qubits and also the couplers, just for purposes of tuning up the gain. And this is some calculation here of effective coupling strength between the 2 different modes in megahertz as a function of the operating frequency of the coupler. The qubits here are resonating at about 4 gigahertz or so. And this is some preliminary data from these devices where you can see that at 0 here, this means the 2 qubits are tuned to the same frequency. And if we then vary the flux bias of the coupler, we can see that for coupler bias to slight negative values in these more or less arbitrary units, there's nothing happening. The qubit is not evolving. So here what we're doing is we're promoting one qubit to the excited state. We're looking at the state of the other qubit that it's coupled to. we're evolving the state of this 2-qubit system for some amount of time. This is, I think, for a couple hundreds of nanoseconds. And if the second qubit remains dark blue, that means it's not evolving, it's not feeling the interaction with its neighbor. But if you tune the coupler to positive bias, you can see that depending on the evolution time, there's some swapping that's going on in positive bias. And so this all makes sense. Again, this is an experiment where we've changed a bunch of things about our device fabrication, but also about the way that we're biasing and delivering control signals. And we're still, I think, pretty confident that with this particular sample, we'll be able to push, close to 10 to the minus 4 fidelity on 10 to the minus 4 infidelity on a Seif gaze-based entangling gate. This is something that we need to do. The coherence times of these qubits, by the way, are about 80 microseconds, which is pretty good given the relatively complex fabrication that goes into these circuits. So this is not a single layer, this is a multi-layer fabrication that involves wiring crossovers and vias, and that more complicated fabrication generally comes at the expense of added loss, because as you add more materials, you're introducing more low energy defect states that can couple with the qubits and just act as a dissipative path. So with very simple single layer devices, we've seen qubit T1 time up to about 800 microseconds. With this more complicated fab, 80 microseconds is a pretty good starting point for us to bring up high fidelity entanglement gates. The T1 coherence limit on gate infidelity, I think, for this device is going to be something like 2 times 10 to the minus 4 for gate times of order 50 nanoseconds, which is what we're targeting here. Okay, so this is how coupling looks in the world of superconducting qubits. In parallel with tuning up this entangling gate on this simple 2-qubit 1-coupler circuit, we're actually already fabricating a device that involves 4 qubits coupled by 4 tunable couplers. So this is not something that we've got fully fabricated yet. This is just the GDS layout that we're using to make the circuits. And here, the white over here is aluminum ground plane. The cross-hatched color is where aluminum gets etched away. So we've got 4 circular islands for qubits. We've got these 4 sort of funky dog bone-shaped couplers, which are, essentially additional transmod modes, but in this case, we're not using those to store quantum information. We're just using those to mediate interaction between qubits. And then the blue that you see, bluish-greenish color, those are crossovers that we're using to stitch together the different parts of the ground plane to ensure, very good microwave grounding and good signal integrity for the control signals that we're applying at 5 to 10 gigahertz to do the operations of these circuits. So this is something that I think we'll have fabricated and we'll be testing probably by end of summer. So, okay. So are there questions about that? I think I've given background to basic operations, single qubit, 2-qubit measurement. Any specific questions? Okay.
Yep. So it looks like the design is very similar to the 2-qubit, and
this is done by E-beam or the laser?
Yeah, the way that we do fabrication right now is, okay, and I don't have a scale right here, but this is a 500 micron grid. So these are big devices. And so we use optical lithography for everything except for the Josephson junction itself. So the Josephson junction is typically 200 nanometers by 200 nanometers, 150 nanometers by 250 nanometers.